All right, let's start. We'll check on the Rangers game at our break, okay? For all of y'all who care. For all those who do not know, we want them to win today.
Yes. Yes, we do.
More so than other times. Okay. So I want to finish this chapter up and work some problems out with it. So we looked over the E2 mechanism right before we left. Which mechanisms have carbocations? SN1E1. Can those rearrange? Yes, so rearrangements goes with the carbocation. Which ones prefer a neutral nucleophile / base? The ones, SN1E1. And which ones prefer negative? The twos. Which one prefers primary? Just SN2, and the others want tertiary, preferably. Okay, and now E2, what does this mean with the mechanism? Does it happen in a few steps, or does it all happen at one time? One time. So you see here, this base here, notice it's a negative base, that negative charge there, comes in, takes the hydrogen, and where does hydrogen leave its bond? The carbon to make the double bond, forcing the leaving group to leave. Okay? Now, for E2 stereochemistry, the only thing, and we'll get more into this in chapter 7, but just know that right now, it likes for the hydrogen and the leaving group to be 180 degrees apart. So let me show you with these Newman projections. So the leaving group is X, and here's our hydrogen. Okay, now think about crowding. So do you see that these two here are 180 degrees apart? That's favorable. And so a base can come in up here, and the leaving group can leave down there. You know, no crowding or anything. Now, whenever they're on the same side, so like this, what do we call this? Eclipse. Is that favorable? No. And you see there's crowding going on there. And on top of that, your base has to somehow fit in here and grab that hydrogen, and your leaving group has to leave altogether. So it doesn't like that. So it likes your hydrogen and leaving group 180 degrees apart. They call that anti-coplanar. Anti meaning they're 180 degrees, coplanar meaning they're just flat. So if I show you, notice how they draw these. You see the hydrogen and the leaving group are 180 degrees apart there. Okay. And again, we'll look more into that, but just know they like to be 180 degrees apart at this point. Okay, so here's some differences between E1 and E2. Oops. I would say the biggest difference, if you're looking at a reaction and you want to know if something's going to be E1 or E2, like you see a double bond's formed, okay? And I ask you, is this going to be an E1 or E2? I would look at the base. Is it a negatively charged base, or is it a neutral base? And that'll tell you pretty much right there. E2 likes which one? Negative, and E1 likes neutral. Okay, so the best thing to do here is to make this little chart that I think could save your life. So you're going to write on here primary, secondary, tertiary. Okay, I'll even use proper colors, red and blue. Okay, tertiary. Which ones prefer tertiary? All except SN2. So if I have a SN1, E1, remember those will always go together. We're just going to say, for our knowledge, you can't really separate them. The only way you possibly could is making the temperature really high, but even then you get a mixture. So for the most part, you can't separate them. So if I have a mixture of SN1, E1, what type of base does it like, or nucleophile? Negative or neutral? Neutral. And then E2, negative. So the first thing you're going to look at is tertiary. You know, if you have a tertiary carbon. Then you look, okay, at your base, is it neutral or negative? And that'll give you the answer there, if it's SN1E1 or E2. Now let's go over to, because secondary is going to be the hardest because everything can go secondary. So let's skip that for now. And let's go primary. Which one prefers primary? SN2. Now I'm going to specifically put on here, well, what charge does it like the base or nucleophile? Negative. It also likes it to be small. Now small would be something like, an example, hydroxide or something. And then I'll show you an example of something large so you can see the difference. What also can go primary? It might not be its favorite, but it's E2. E2 can go primary. What charge base does it like? Negative. Okay? But if you want it to be just E2, let's look at SN2. They both want a negative base or nucleophile, but SN2 wants it to be small. So how can I make it not one SN2? I can make it large. An example of that would be OC CH3 3. So do you see right here? I have 3 methyls branching off this carbon here. So this is a big base. If I drew it all out, versus just OH minus. Pretty much anytime you have 3 branches, so you see this parentheses 3 there, that's what you look for, and that'll mean that it's large or bulky. Okay, now let's look at secondary. Now if I have SN1, E1, what charge do I want there? Neutral, right? What if I wanted only E2? So what charge do I want the base? Negative. And if I want to make sure it doesn't go SN2, I would want it large. Let's see. Then we could, another possibility is a mixture of SN2, E2. So what charge? Negative. And in this case, it's a small base. Now the difference between these two here is that what does SN2 prefer? What's its favorite type of carbon? Primary, right? So, and it prefers no crowding at all. So these are the ideal This is the ideal situation for an SN2 reaction. You have a really small base because you don't want it to be crowded, and the carbon's primary. So that's perfect. This is everything that goes with SN2. Now over here, does it like secondary? It's kind of like, I'll go, but it's not its favorite, right? And E2, what does it prefer? Tertiary, okay? So basically what happens here, since the situation is not ideal for either one, basically the small base will go for either one. Now for sure the large base won't go for SN2, because what's the big driving force with SN2? Crowding, okay? So do you think crowding, that's the key thing with SN2. So do you think it would ever want a very large base there? No, because it'll get crowded. So no matter what, it always wants something small, okay? But when I get over here, it's not as, what's the word I'm looking for? It's not as picky, I guess. Okay, so then the last one is we could have SN2 only. Now this is one you haven't seen before, and that's why I'm going to bring it up. This is whenever you have an like an iodine nucleophile. This really only works with iodine. Now the reason iodine, so going to the right and down makes you more acidic, okay? How far to the right is iodine? All the way to the right, because we ignore group 8. They're not reactive, okay? So for reactive atoms, this is the furthest to the right. And then how far down is it? Pretty much all the way down, right? So this is acidic. Well, not acidic, but it's more like an acid. So do you think it's going to be very basic? No, because the trend is it's acidic, okay? So this will not act as a base at all. Or your eliminations, you have to have a base because it takes off a hydrogen. So since this cannot act as a base at all, it can go SN2. Because it's negatively charged and it does have lone pairs, it can act as a nucleophile. Because a nucleophile, does it take off a hydrogen? No, it makes a bonded carbon. So because of that, it is negatively charged, so it is reactive, but it will act as only a nucleophile and not at all as a base. Okay? So this is the chart. I would memorize this, and let's see how to use this. So let's do some examples. They have some here. Okay, let's look at this. Tell me what kind of carbon you have. Tertiary. And then what else do we have? What's over the arrow? Neutral. So we have tertiary, neutral. So we come over here. Tertiary, neutral. What's the answer? SN1E1. Okay? So if I actually write out the answer to that one, let me remember what it looked like. It'd be like this. Okay, so here's the reaction. What is going to leave on here? Bromine. And what will take its place? What? Yeah, which atom will actually be bonded to there? O. So OCH3. And which one was that I just did? Is that an SN1 or an E1? SN1, right? Did I make a double bond? No. Your E's will always make a double bond. So then we also need to draw the E1 because we said it was SN1E1. Okay, so here's where my leaving group is. Now I need to decide where my double bond will go. What type of carbon is this, we said? Primary, secondary, tertiary? Tertiary, so that means there's 3 choices. So I can go to methyl, I can go to this side of the ring, or I can go to this side of the ring. What do you think? Which one is it not? The methyl, right? Because you want a longer chain. Do you see that this side of the ring looks exactly like that side of the ring? There's really, you can see CH2, 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 and they both meet at a CH2. So you can go on either side. So let me just draw it. Is the bromine going to be on there anymore? No. So here's my methyl. That's where the bromine was, and I'm going to go towards the top of the ring. And you could have had it going down if you wanted. But the only wrong choice would have been going towards the methyl. All right, let's look at another one. Why wouldn't I what? To which one? Because E1 only, it doesn't add the nucleophile, it only makes a double bond. By definition of elimination, if you look at the mechanism, what happens here, in the first step of your ones, what's the first step? Leaving group leaves. And we're going to do the E1, not the SN1. And what's in its place? What's on that carbon now? A what? What charge? Positive. Okay, so I have my leaving group gone. Now, what do I want to do here? So if it was SN1, this oxygen would come make a bond there, right? That's what we see right here. But it doesn't do that. It makes a double bond. So what happens? What does this oxygen do instead? Takes the hydrogen off. So it's going to come over here, grab hydrogen, and then what happens to this bond? It becomes a double bond, right? And that's E1. So that's what happens. The oxygen doesn't add because then that's the substitution. So any of your eliminations, you're forming the double bond, and that's it. So leaving group leaves, form the double bond. For your substitutions, you don't form a double bond. You add what's over the arrow, basically, to it. Because you're substituting the leaving group and what you put in there. Okay, so let's look at another one. Okay, what's this one? So what type of carbon do we have? Secondary. That will always be your first question, or should be. So secondary. So that's the longest list, so that does not help at all. Okay? So then we look on here, what's over the arrow? Something negative. We also have something neutral, but always ask which one's more reactive, the negative or the neutral? The negative, so that's the one we care about. And remember, sodium means that this is actually a negative charge. It's masking your negative charge. It has no point of the there's no point of it in the reaction except to neutralize it, okay? But that is actually a negative charge. Okay, so I have a negative with a secondary. So what do we know it's not? It's not SN1, E1, because those only like neutral. Okay, now I need to look on here. So let's come over here to my chart. We know it's not this one because it's not neutral. Is it over the arrow? Do I have an iodine? Iodide, actually? No. So then I just need to decide, is this large or small? So does it have 3 branches coming off of it? How many methyls does it have coming off of it? 1. So does it have 3? No. So this one's considered small. So it's small and secondary. So our answer is SN2 and E2. So let's look at this. This is why this chart, you know, this one forwards and backwards too. You predict which one it will be. So if I draw this one, we had CH3, CH, BR, CH2, oops, H3. And I'm just going to put OCH3 right now. Okay, what will the SN2 part look like for our answer? What's leaving? Bromine, and what takes its place? OCH3. Oops. OCH3. Okay, so for your substitutions, leaving group leaves, and then put on there what's over the arrow. But what about E2? What do you always make with your E's? A double bond. So now we need to decide where the double bond will go. So here's our leaving group. It can either go to the left, which is towards a methyl, or to the right, 1, 2, 3, 4, which is towards like a butyl. Which one will it go towards, left or right? Right, because that's the longer chain. Now in the mechanism, what do I take off right here? Hydrogen, so just remember to do that in your final product. So is the bromine going to be on there? Nope. So right there, you see it's on a CH, and put a double bond. And now what is it bonded to? It's not actually a CH2, it'll be bonded to a CH because I'm taking that hydrogen off. So your E's always make a double bond. And you just need to figure out where that double bond goes. And then your S's always do a substitution. They'll put your nucleophile on your product. Okay, now I'm going to pull up part of lab maybe 8. Is that the one that does SN1, SN2? 9? Okay, 9, whichever one that is. Now, as a group, so this part right here, this is number 12. See if you can figure these out. I do want to tell you that, do you see how this isn't necessarily over the arrow? That's okay. Let me explain that before you do this. If I have something like this, you know, blank, that means the same as or I could do it like this. Anyway, the possibilities are endless here. Anyway, so the point is, sometimes they'll do a plus sign. Sometimes they'll put it over the arrow. That means this and this are reacted together. Sometimes you see over here, they have kind of a mixture. You see they have this plus this, and then over the arrow you have this. Okay, there's just everything on the left of the arrow is just everything you're adding. Okay, so it's this plus this plus this, and that's your temperature. Okay, does that make sense? So don't let that arrow, don't let that this is, you know, under the arrow, but that's to the left, and don't let that confuse you. All of those are being added in one beaker. Okay, and it doesn't even matter if I put it at the top or at the bottom. Okay, that means the same thing too. These are all your ingredients you're putting in your mixing bowl. Okay, and it doesn't matter really what order because they're all going to go in there at one time. Okay, so kind of, then also before you begin. Toluene is just a solvent, and it won't really affect your reaction. So don't let that one affect you. Okay, so as little group, see if you can figure these out. So I want you to tell me, is it SN1, E1, SN2, E2, or is it a mixture of them? Tell me that, and then also write the product out. And then we'll check them here in a few minutes. look at these a little bit. Okay, right here. What type of carbon do I have? Tertiary. And what kind of base/nucleophile do I have? Negative, right here. It's sodium hydroxide. Remember, if you see sodium, that means it's negative. Okay? Water's in there, but that's neutral, so it doesn't really matter. Okay? Because I have a negative and a neutral, negative ones. Okay? Now, what will this be then? E2, because it would have to be neutral for it to be SN1E1. Okay, now where will the double bond go? Because we're doing elimination, so you make a double bond. Here's the carbon. I can go towards methyl, methyl, or ethyl. Ethyl, so you're going to make a double bond between those two carbons. So I look something like this. And how many hydrogens on that carbon there? CH, CH3. What was it? E2. Okay, let's look at the next one. What type of carbon do we have? The type of carbon you have is the most important factor in determining all of this. So what do I have? Primary. So what can it not be? A 1. Now we look at here. It is neutral, right? But it doesn't matter because it's primary. So then I look at, is this small or is it bulky? Or large, bulky? Large. Why? There's 3 carbon groups coming off of there. Do you see that? There's a subscript 3. So what is this? E2. This is a primary, so there's really only one place to put the double bond, which is between those 2 carbons. So it look like, does it matter what? Yeah, you have to get rid of the side that the leaving group was not on. So you would have CH2, double bond, CH. I don't remember the rest of it. What, CH2? There's CH? I don't know. Then I think there's a branch or something. Something like that. The point is, the double bond is between the 2 carbons, and you always take the hydrogen off where the opposite of the leaving group. So the bromine was right here, so you take the hydrogen off the other carbon. Okay, now let's look at the last one. So it's between these right here. So you should have CH3, CH, CH3, CH, CH2. So I think I added another CH2 in there. Anyway. Okay, what about this one? What type of carbon do I have? Secondary. And then what is it reacting with? Not iodine. Iodine's already on there. That's a leaving group. Oh, CH3. If iodine was reacting with it, it would be like listed over here somewhere. Like it would be like I minus. Right? We don't care about iodine as a leaving group, as iodine is a nucleophile. Okay, so OCH3 minus. So and then is this considered small or large? Small. So I have a secondary, a negative small base. SN2E2. If iodine is the nucleophile. If iodine is the leaving group, that doesn't matter. So it would have looked like, I'm going to put bromine because it wouldn't have an iodine leaving group. Something like this. Do you see where now it's reacting with iodine? And so then you would just put the iodine on there. But that's not what happened. And this iodine is actually my leaving group, not my nucleophile. It's already bonded there. So I have iodine here. So that's a leaving group. And then over here I have OCH3 minus. So this is what's reacting with that. Okay, so we said since we have a secondary negative small nucleophile base that this is SN2 E2. Now what would the SN2 look like? Yeah, then the OCH3. And then what about E2? What does it always make? Double bond. So my iodine was right here. Now I can make it a double bond going to the right or to the left. Does it matter? No. There's more of these on the homework and everything. Also in the textbook, you probably don't have, you might have textbook, I don't know. But if you don't, it's on reserve in the library. And at the very end of this chapter, they have some sort of example problems at the very, very end of the chapter. Okay? And I think it's like highlighted in green or something like that. Anyway, those are also good examples. And so what you could do, if you wanted to look at those, you could go to the library, grab the book, and you could just make a copy of those couple pages. And what they do, it's like example problems. So it has like, you know, this reacting with this, and then you have to guess what the answer is, and then it explains the answer and everything for you. Okay, so it has kind of a question and an explanation underneath it. So that those are good too. And again, that's at the end of the chapter. So it's like, what chapter is it? Chapter 6. So it's the end of chapter 6, and it's before they actually have the homework problems. You know, like every textbook has some additional kind of homework problems you can do. It's before that and at the end of the actual text. Okay? Does that make sense? So before the homework problems, and it's actually the end of the text part of it, there's some additional problems that are nice because they have them all worked out and everything for you. Okay. So that is chapter 6. So for this chapter, know the difference between SN1, SN2, E1, E2. When do they occur together? When are they separate? Know the mechanisms, how to draw those out. Know the conditions that they like. So that other chart we made where, you know, when is something, the order is secondary versus primary. What does the energy diagram look like? You know, does it for a negative or a neutral base? Anyway, stuff like that. So that's chapter 6. And tomorrow, the second half of class, we'll go over the review. Okay? So we'll work out some more problems with 5 and 6. You can bring some questions you might have, I don't know, homework or lab. And in addition, you know, maybe you don't necessarily have a specific example, but if you have a topic, you know, like I'm really having trouble deciding if something's R or S, you know, let me know, and then we'll do some more problems over that. Okay, so you can bring, you know, a specific question or just a topic, and we'll work out those problems, okay? And even if nobody brings anything, that's fine. I'll have problems in my head that will work out, okay? So let's take a break, and then we're going to actually start chapter 7. go ahead and start back up. All right, let's go ahead and start chapter 7. We need to get through at least a little bit today. So, chapter 7, what we're going to be looking at is the structure and synthesis of alkenes. So what's an alkane? Carbon with all single bonds. Yeah, hydrocarbon, all single bonds. An alkene is a carbon structure with a double bond. So we're going to look at the structure of double bonds, and synthesis, that means how do we make them. Now we've already learned how to make them. How do we make them? Elimination reactions, E1s and E2s. So they're just going to kind of go a little bit more in depth into E1, E2 in this chapter. Okay, we've already done it. You just need a leaving group and a base. Okay, and you can make a double bond. Let's look a little bit into the structure. Oops. So again, these are hydrocarbons. What does hydrocarbon mean? Hydrogen and carbon. Okay, hydrocarbon with a double bond. The double bond is reactive, and this is one of your first kind of real functional groups, an alkene. Sometimes alkenes are referred to as olefins. An olefin is an alkene. Okay, so if we look at the structure of a double bond, all right, what's the hybridization of each carbon? sp2, right? Because you have the double bond. Anytime you have a carbon-carbon double bond, both of those carbons are sp2. Now, if between on this bond, only the double bond, how many sigma bonds do we have? One sigma, and the other one's a pi. Your pi bond is actually the reactive bond. It's not quite as strong as a sigma bond, because the sigma bonds, remember, those are hybridized. So your sigma bond is a sp2 orbital. So do you see it's a combination of an s and two p's? Okay, so it's kind of like on steroids, if you want. Now a pi bond is made only from a p orbital. Okay, it's not hybridized or anything. So you have a p orbital or a hybridized sp2 orbital. Okay, so the p or pi or bond is always going to be a little weaker. So that's the bond that actually reacts. Okay, a functional group is basically a reactive group. That's all it is. And there's classifications we're going to look at, in this case, alkenes, double bonds. Chapter 9 looks at alkynes, which are triple bonds. They're alcohol groups, which are OH, aldehydes, ketones. Anyways, we'll go over most of the functional groups in organic too. But right now, we're looking at alkenes. And so anytime we talk about a functional group, that's just a reactive group. So anytime you see these groups in a compound, they could react. Okay? So we're looking at double bonds, and the pi bond is what reacts there. Ethylene is actually produced by plants and trees. And whenever it produces a lot of ethylene, it basically triggers the plant or the tree to lose its leaves and stuff for fall. So ethylene is important for plants. So we just talked about this a little bit. So sp2, what is the shape that goes with sp2? Trigonal planar. So it's flat, right? It's planar. And the angles are 120. Trigonal, like a triangle, 120 degrees. Okay, the only thing that's important for this slide right here is look at the length of a single bond, 1.54 angstroms. Angstrom is just a unit of length, okay, kind of like an inch or a centimeter. And then over here, 1.33 angstroms. So which one's shorter? The double bond. Double bonds are always shorter than single bonds. And which one do you think is stronger overall? A single bond or a double bond? A double bond, think of you have two bonds. I know one of the bonds isn't that strong, but you have two of them stacked up between one. So a double bond is shorter and stronger. Think about, have you ever, maybe when you're a little kid or something, you had the straw, and you try to like cut the straw with your hand or something. Now, whenever it was longer, it wasn't that hard to do, right? But what about when it got really short? You know, you're over here. Was it harder to break? Yeah. And so just think of it that way. So when you're shorter, it's stronger. It's harder to break that bond. And over here, you're longer. It's easier to break. Okay, we just talked about that. Cis and trans. Can I rotate a double bond? No. So if I converted a cis to a trans, I would have to actually break one of the bonds, right? One of the double bonds, switch it over, and then put it back together, right? So without breaking a bond, I cannot actually convert between cis and trans. So that's what we have the naming cis and trans. And just a refresher there, remember, let's see if they have a picture. No. Here, that you can only have two groups comparing. So hydrogens, we don't care about hydrogens, okay? They're like nothing to us, okay? So over here, how many non-hydrogens do we have coming off this double bond here? Two. I have a methyl and a methyl. Yeah, there's blue and the green that's supposed to represent the double bond. Okay. So I have two methyls. So do you see two of them? Also notice that they're on different carbons. That's a requirement also, okay? If I have both of the methyls over here, so let me show you something like this. This does not have cis or trans geometry there because they're on the same carbons, okay? You have to have them on different carbons. Okay, so what would this one be? Cis, okay? And if I flipped one of them, it would be the trans. So you can only compare two things, and let's look at that too. If I had something like this, okay? Now I have a methyl. How is it compared to the chlorine? Cis compared to the chlorine, and then FL. And what about the fluorine? Trans. So what do you write in the name? Cis trans, trans cis, whatever. You can't determine that because it's both cis and trans. So the requirements to use cis trans, you can only be comparing two things. You know, if this was a hydrogen, then I would only be comparing those two things there, and that will work, okay? So you can only compare two non-hydrogens, and they have to be on different carbons, okay, to have cis trans. And that'll help you for your lab for 8. Your lab also brings up E and Z. We'll go into more into naming here in a minute. So if I redraw the one I had here. Okay, so can I draw, or can I say cis or trans for this one? No. So what we have to do is use a different naming system called EZ, okay? E is just like a trans, and Z is like a cis. Now how you determine these, you cut it down the middle here, so kind of like the left side, right side. So you see I'm cutting the two carbons. I'm not cutting them this way. I'm cutting them through the middle, like separating the two carbons out. Now what you do here is you base it off priorities, just like you would do RS. Okay? Now looking at RS configuration and the priorities, what would be a higher priority, methyl or hydrogen? Methyl, so that's priority 1. Now over here, chlorine or fluorine? Chlorine. Do you see that my number 1 priorities are on the same side? So that would be Z. It's a larger weight, basically. So that's how you do EZ. It's in the lab. So you just split the two carbons in half, the left carbon to the right carbon. And then you do the priorities like R and S, and you just need to figure out which one would be number 1. Your number 1's on the same side. Or what if I had a 1 and a 1 like that? Then it would have been a E, or trans. Okay, so then the next concept, and we'll go more into naming here in a second, would be elements of unsaturation. Okay, when something's saturated, that means you have the maximum amount of whatever you're looking at. Okay? In this case, a saturated compound, we're looking at hydrogens. Okay? So if I have, for example, ethyl. So CH3, CH3. This one's fully saturated with hydrogens here. I have a total of how many? 6. So anytime you have an alkane, so single bonds, you're fully saturated. Now let me show you a ethene. CH2, double bond, CH2. Now how many hydrogens do I have? 4. So am I fully saturated with the maximum amount of hydrogens I could have? No, the max would be 6. But I can't even have 6 because of the double bond. So anytime you have to take away hydrogens to add a bond, you lose saturation. So we say that that's unsaturated. And anytime you lose 2 hydrogens, so you see between here and here we lost 2, we call that 1 degree of unsaturation. Or, if you want to say, you lost 2 hydrogens. So how many degrees of unsaturation right here between the two? 1. Now let's look at a triple bond. So CH bonded to a CH, we'll say. How many hydrogens do I have here? 2. Now going back to the original, which was 6, how many degrees of unsaturation? 2. So for every 2 hydrogens, that's 1. So how many hydrogens did I lose? 4. So 4 hydrogens, so for every 2, that's 1, so that'd be 2. Okay, so which one is the most saturated? The other one with the 6. And what's the least? The bottom one with the triple bond. Okay, so every time we start adding multiple bonds, you start losing hydrogens. The other thing that does that would be rings. Let me show you why. So let's look at propane. CH3, CH2, CH3. So how many hydrogens here? 8. Okay, now I'm going to draw a cyclopropane. So still 3 carbons. CH2, CH2, CH2. Or if you want, you can. Okay, now how many do I have? 6. So how many degrees of unsaturation did that take? 1. So that's what it means. So basically, every time you have to lose 2 hydrogens to make an extra bond, we call that a degree of unsaturation. And there's a formula to calculate that. So if we have this formula here, C5H8. C5H8. Okay? Now, just by looking at that, you have no idea what the structure is, right? There's several ways. There's different isomers you could draw here. Okay? But from the formula, you can get how many degrees of unsaturation. So what you can do here, here's the formula. 2 times the number of carbons plus 2 minus number of hydrogens plus halogens minus nitrogens, all divided by 2. I think when you do the homework, not that you're going to do it like today or anything, but the formula they give is slightly different because they distribute the negative out here, and so they have a plus, negative, negative, plus. Anyway, that doesn't matter. My formula is the same as their formula, okay? They just multiplied everything by -1 there, okay? But just so you know, they're the same. Look at the same answer. Okay, so let's look at this. My molecular formula there is C5H8, and I want to know how many degrees of unsaturation do I have. Okay, so let's plug it into this formula. 2 times how many carbons? 5 plus 2 minus how many hydrogens? 8. Do I have any halogens? Do I have any nitrogens? No. Divided by 2. So 2 times 5 is what? 10 plus 2, 12, minus 8, 4, divided by 2, 2. So I have 2 degrees of unsaturation. Now let's think about what this tells you. So how many hydrogens have you lost there? 4 total hydrogens. So let's think about this. A double bond has how many degrees of unsaturation? 1. A triple bond has how many? Not 3, but 2. And a ring had 1. So those are really your choices we're looking at, either a double, a triple, or a ring. Okay? Now, this says it has 2 degrees of unsaturation. We have no idea what that's due to. We just know that it has 2, and it lost 4 hydrogens. So if you look at here, that could mean that I have a double bond in a ring, right? Because what does that add up to? 2. Or I could have just 1 triple bond. Or I could have 2 rings. Or I can have 2 double bonds. I mean, I'm not going to sit there and make you, tell me every single, combination possible. But do you see here that what I do know is that I'm either going to have multiple bonds or rings in this structure. And that's about all you can tell me. What's nice about this, though, so sometimes when you're in the lab and you can do analysis and you can see your ratio of carbons to hydrogen is 5 to 8, so C5H8. And you're trying to figure out what does this structure look like. You have no idea. The first thing you could do is calculate the degrees of unsaturation. And at least could do something, okay? Because before this, I didn't even know there could be double, triple, or rings in there. But now that I calculated, I see that it is possible. So I need to consider that whenever I'm analyzing the structure, okay? In Organic 2, we're going to be looking at some of the machines that actually analyze your products so you can tell what they are. And this will come in handy here, degrees of unsaturation. So what this tells me, this molecular formula here, this compound, has 2 degrees of unsaturation, so it has some combination of multiple bonds or rings. Okay? Now let's look at another one. Let's do C4H7Br. Okay, let's figure this out. I have 2 times how many carbons? 4 plus 2 minus how many hydrogens? 7 plus how many halogens? 1. Nitrogens? 0. Okay, 2 times 4, 8 plus 2, 10. 7 plus 1, 8. 10 minus 8, 2. 2 divided by 2, 1. So I have 1 degree of unsaturation. So which one could I not have? So I have double bond, ring, and triple bond. Triple bond. There cannot be a triple bond in here because how many degrees of unsaturation does it take? 2. So I know in this structure there's either a ring or a double bond. Okay, so work together and see if you can figure out this one. This is actually the molecular formula for Tylenol. The score is 1 to 0. A's. Okay, I have 2 times how many carbons? 8 plus 2 minus what? 9 minus 1. Are there any halogens? No. Did I put oxygen in the formula? No, so don't put it in the formula. Divided by 2. So what do we have here? We have 2 times 8, which is 16 plus 2. 9 minus 1, 8. 18 minus 8, 10 divided by 2, 5. So let me show you the actual structure, and let's see if that makes sense. Okay, so that is the structure of Tylenol. Now, how many degrees of unsaturation do I have here? 5. So we should be able to count 5 on here. Okay, how many rings do I have? 1 ring. How many double bonds? 3 and 4. 1, 2, 3, and then 4. So I have 4 and 5 for the ring. Do I have any triple bonds? No. So I have 1 ring, 4 double bonds, which equals to what? 5. Now you couldn't have predicted that. There's no way I could give you that formula and you see there's 5 degrees of unsaturation and somehow you could draw that. There's no way you could do that. But do you see that the two match up? That there are 5 degrees of unsaturation because of the ring and the double bonds. Okay, so the last thing we're going to do today, and then you can go, will be naming. And naming's not too bad. Okay, so everything we named before would be like pentane, butane, ethane, propane, right? And the parent name. But we're not looking at alkanes anymore. We're looking at alkenes. So how do you end it? Ene. So you'll have like butene, ethene, pentene. You know, the name, it goes on. Anyway, so instead of ending in A and E, you will now end in E and E. The other thing that changes slightly from the rules is that your double bond is the highest priority we've seen so far. Meaning, whenever you're numbering, you're going to start counting the end where the double bond is closest. Okay? Don't look at the branches because they're not going to matter. It's where your double bond is at. Okay? So you're going to start numbering at the end where the double bond is the closest to. The other thing is on a ring, since the double bond is the highest priority, it's going to start on carbon 1. You know, on a ring, we can start carbon 1 anywhere, and it's going to start with the double bond. So let's actually look at some examples. Okay, I know you can see, pretend you can't see the answers down here. Okay. How many carbons? 4. So what do we call that? Butene. Okay. Now, if I'm going to number this 1, 2, 3, 4, or 1, 2, 3, 4, where does the double bond come in? It starts on which carbon? 1. Why don't I say it's 4? It's closest to the other end. Okay. Now I have to say where that double bond is, because if I didn't tell you, if I just said butene, you could have put the double bond right there, or you could have put the double bond right there. Okay, so that doesn't help you. So just kind of like where your branch is, if I didn't tell you where a branch was, you would have no idea. Okay, so you have to tell me where the double bond goes. So in this case, 1-butene, meaning the double bond starts on carbon 1. So let's look at like this one right here. How many carbons there? 5. 1, 2, 3, 4, 5. Where does the double bond start? Starts on number 2. So we say 2-pentene, meaning We have a double bond in there because we see in our name that it's ene and that it's going to start on carbon 2. Now you can have branches, so if I have let's say something like this. How many carbons in the longest chain? 5. So we name that as a pentene. Where is the double bond? 2. 1, 2. What are these branches called? Methyl. And we have 2 of them, so we call it dimethyl. So that's carbon 2. Then where are my methyls? 2 and 4. So the only things that have changed are now we're going to end the name in ene because we're adding a double bond in there. And we have to say where that double bond is just like we would any other branch. And double bond has a priority over the branches, so in numbering. Okay? So if the double bond was over here, then it would have started on carbon 1. Okay? So double bond has the highest priority, so it gets numbered first. And then we could look at this like a ring. Okay, how many carbons in that ring? 6. So I would call that cyclohexene. Okay, now here's the part with the numbering. So instead of calling it cyclohexane, I call it hexene because it has a double bond. All right, now the carbon, their double bond has to be carbons 1 and 2. Okay, so it's either going to be counted as 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6 all around. It's always the shortest pathway. So you have to go through the double bond because double bond is 1 and 2. So these carbons are 1 and 2 no matter what. Now it could be 1, 2 or 1, 2, but they both, does that make sense? They have to be 1 and 2. So you have to go through the double bond, and then to decide which one is number 1, this one or this one, it's just the shortest path to your branch. So 1, 2, 3. Okay, so where, well, I don't actually have to put where the double bond is because it's always carbon 1 on a ring. But where is that branch? 3. So 3-methyl cyclohexene. Now, why did I not put a number for the double bond? It's always carbon number 1. So let's go backwards. Let's say I'm going to draw 3-methyl cyclohexene. Okay, so I go backwards. Cyclohexene, what does that mean? Cyclic. And ene means double bond. Now, here I haven't set where carbon 1 or 2 or anything is, so I can put my double bond anywhere. So just to prove a point, I'm going to put it right here. Now, where's my methyl? Carbon 2. So I can count 1, 2, 3 and put it right there, or I can count 1, 2, 3 and put it there. Either one's correct. Both of them are 3 away. So I'll just put it right here. Now you see, it looks a little bit different than what the other structure was, right? But if we go back and name it, you see this is a cyclohexene. Do we agree with that? There's a double bond in there. Now this has to be on carbon 1 and 2. So what's my shortest pathway? That would be 1, 2, 3. 3-methyl cyclohexane. Okay? So remember, this, if I gave you this and, what was it over here? This, that's a double bond in here. And I ask, are those isomers? Just by looking at them, what do they look like? Possibly, right? You know? But then you name them. Do you have this the same name or different name? Same name, so they're actually the same exact structure. If I rotated this one, over kind of like that, it kind of starts turning into the other one. Anyway, so they're the same structure. If you have the same name, it's the same structure. Now, if I would have moved this branch over here, now it's on carbon 1, 2, 3, 4. Now, are they different? Yes, now they're isomers. Okay, and we can also do cis and trans. So how many groups do you need for cis trans? 2. So we could have So do you see that I'm actually showing the direction of the methyls? Like if they're pointing up or down? Okay, so how many carbons in the longest chain? 4. 1, 2, 3, 4. So what do we call 4? Butene. And where is the double bond? Carbon, yeah, so it starts on carbon 2. Are there any branches? No, because we included all of this in the chain. 1, 2, 3, 4. So are there any branches? No, but I can label this double bond as a cis or trans. And what is it? Cis. So at the very beginning of the name, you had to put cis-2- butene in this case. So cis and trans goes at the very beginning of the name. So name everything like you would, and if you can see cis or trans, then you put it in there. And how do you know if you can see cis trans? Let me show you this where you can't see it. Okay, that's the same exact compound. That's butene, 2-butene. But can I tell if that's cis or trans? No, because I don't know if these methyls are pointing up or down, opposite, the same. I have no idea. So here I could not put cis or trans. I could just say 2-butene. But do you see when I actually draw the bonds coming off the double bond? I'm showing, the direction. Then I can put cis or trans. Do you see the difference? Okay. And the very last naming thing, and then we're done, is E or Z. So we already know how to do EZ. Okay, so before we name this, tell me if this is an E or a Z. What was it? E. So let's look at our priorities. So here's where I half it between the 2 carbons, separating them. What's a higher priority, methyl or hydrogen? Methyl, chlorine or bromine? Bromine. So this is an E. Now we need to actually name it. What's the longest carbon chain in this? 3. Right here? Right, because those aren't carbons. So how do I say 3? Propene. Where is the double bond? Carbon 1, right? So I could go 1, 2, or 1, 2. So it's actually in carbon 1. Did everybody see that it's on carbon 1? Since that's the end there. Okay, now I need to add, do the rest of this. This is called what? Chloro. This is bromo. Any other branch? No, because we don't include hydrogen, or we don't care about it at all. So what comes first, bromine or chlorine? Bromine, so I'll have bromo, chloro, and where are those? They're both on which carbon? 1. Okay, now if I was doing cis or trans, where do I put it? At the very beginning of the name. But if this isn't cis or trans, this is E or Z. Why is it not cis or trans? 3 different groups coming off of there. This will also work at 4. Okay? So what do I put at the beginning of the name? E. So just kind of like if that was trans, you just put E at the very beginning. And just like cis or trans, the only way you know if something's easy if I actually draw the bonds out. Okay, so if they just have it in a line, you can't tell. All right, so we'll end here, and tomorrow we'll look a little bit more into E or Z. Really?